We want to take a look at this other structure on the day 10 slide 2. Here we have an ethyl group with a solid wedge and a chlorine with a dashed wedge. They're on 1, 2, 3, carbons 1 and 3, or if we number the other way around, 1, 2, 3, 1 and 3 here. So these particular atoms are pointing out in space. I want to make a model that reflects this so we can analyze what the chair should look like, and so we can draw the chair for that and look at the stability of the two different possible ways that that chair can rotate or do a chair flip in space. Okay, so to make the molecule we just saw, there was an ethyl group pointing out at you at the top of that ring, so I'm going to connect that there, right here. I'm starting with my ring flat, because I know if it's flat, anything pointing out at me is a solid wedge, anything pointing away is a dashed wedge. So on that top carbon, there was an ethyl group pointing out at you, and then 2 carbons away, there was a chlorine pointing away from you. So we'll install that there, pointing away from the viewer of the video, right? Okay, so now my ring part is flat. I know that's not stable because of the torsional strain and the angle strain. And so I want to make this into a chair. So again, I'm going to take every other carbon on the top and grab their hydrogens and start pulling those together as I pull the other atoms on the bottom together. Sometimes it's not a hydrogen if there's something substituted there. As soon as I do that, I notice, even though on the bottom it's relatively stable because the only groups pointing straight down are hydrogens and their electron clouds are small enough not to repel too much, on the top of the ring, this ethyl group is in an axial position. So that's really pretty unstable. So what would that chair look like? To draw this into a chair, I want to kind of take my model and make the ring part look relatively flat. Well, it's clearly not flat because not all 6 atoms of the ring are in the same plane. If it was, it'd be much less stable, as we've been talking about. So I see here my ethyl group's in an axial position pointing up from this carbon. So I want any atom or grouping of atoms pointing straight up from the ring to be shown pointing straight up from my chair. And the chlorine is kind of back here pointing away from you. It's pointing off to the side, slightly down at an angle, on a carbon that's 1, 2, 3 carbons away from the carbon that the ethyl group is on that was pointing out at you. So when I make my chair of that on paper, I've got the ethyl group pointing straight up off of one carbon. It's in an axial position. And then 1, 2, 3 carbons away, the chlorine's kind of pointing down and to the side. So that represents that particular molecule, the chair version of that structure. So I wanted to put the actual original structure on there so you could see it too, but I'm noticing that in the video, the way I have it set up, the letters are backwards because of the reflection nature of the video. So that's going to throw things off a little bit three-dimensionally, but you can still get the gist of this. So my ethyl group's pointing straight up off the ring. It's coming out at me if I'm looking down from the top of the ring, which is what this perspective is showing. But notice that anything with the solid wedge always points up from the ring. Anything with the dashed wedge always points down, either straight down if it's an axial group, or in this case equatorial is kind of down and out at a slight angle. So we made our model of this one. Now we want to flip the ring, not like a pancake, but to do the ring flip rotation of the single bonds. So take the head of the chair and push it down to make a temporary boat. And we'll take the feet of the chair and push that up. And I've got, again, 3 axial groups on top and 3 axial groups on the bottom pointing straight up and straight down. That's a good way to check that your model looks right. You should have 3 groups pointing straight up and 3 groups pointing straight down. So now I can see my ethyl group here is in an equatorial position. It's pointing out from the ring. It's not straight down. It's not straight up. That's ideal for it because it can still now kind of rotate a little bit without creating too much repulsion between its electron cloud and the electron cloud of other groups on the ring. So how do I draw this one into a chair? Well, I've got the chlorine pointing straight down, so I know it's in an axial position. That's better than the ethyl group in an axial position. It's not as crowded. But I'm going to have that coming straight down. And then 2 carbons away, I've got the ethyl group pointing out slightly. It's pointing out and up a little bit. So I want that to be represented in my chair. So here's my model. I've got the feet of the chair down here where the ethyl group is connected. I've got the head of the chair up here. This chlorine is pointing straight down. So in my model, or in my picture of the chair, that would be the situation, right? The feet of the chair had the ethyl group pointing kind of out and slightly up. That's an equatorial group. And the chlorine was pointing straight down from that other carbon into an axial position. So now I've got these 2 chaired versions, and I might ask you to assess their stability. If you're looking at the stability of a chair, the main thing you're concerned with is how bulky is the group in the axial position. And you want the rotation that puts the bulkier group always in an equatorial position. So here I see this is my ethyl group. It's in an axial position. It's going to crowd out the other hydrogens that are also in axial positions, here on this carbon pointing straight up and here on this carbon pointing straight up. On the other structure, I just have the chlorine pointing straight down off of this carbon right here. And it's going to crowd the hydrogens that are also pointing straight down from the ring. But the chlorine is just a single atom. It's not 4 atoms like a methyl group is, and so it's not going to be crowding nearly as much. So this structure over here would be more stable, and the vast majority of the molecules would exist in this form versus in the form where I've got this ethyl group, which is a pretty big group as we saw in the model, crowding things out. So that's the value of the model, seeing the size of the groups and the crowding that results, and using the model to help you put the substituents, in this case the ethyl and the chlorine, in the right positions 3-dimensionally.